Hey everyone, welcome to the last lecture of ME154, and this will be a discussion on the remaining topics on bearings. Now, for this part of the lecture, we'll be talking about um, the relationship between reliability and design load life parameters. And after that, we'll be talking about the accounting of actual loads. Oh, okay. We'll be talking about the accounting of the actual loads when we are trying to calculate for the catalog load rating. So in fact, we can actually put in actual loads even though we're technically only considering the radial loads. So we'll talk about that later. Now, as a review, we talked about two topics when it comes to bearings. The first is the load life curve. So the load life curve discusses or rather, it focuses on the effect of having different loads on your bearings for the same level of reliability. Again, reliability is just the assurance, or at least the statistical assurance, that most of your bearings, or at least bearings, a certain percent of your bearings will pass given a particular specified life. So these lines here, these load line curves, they're essentially projections of different loads for the same reliability. So for example, you could be expecting only 90% reliability, or in a sense, 90% of your bearings will be okay by a certain point, by a certain life. And this is described by the following relationships. This is the load line equation. So this is the first topic. And then the second one is reliability itself. This is the function that describes how much of a given batch will survive under different reliabilities. So by default, the load line curve, or at least in the brochures, the load line curves assume 90% reliability. So in case you want to explore um, higher reliability tolerances, then we have to find a way to connect this load life curve, which has different loads, same reliability, to the reliability concept. And to do that, we have to do a few steps. So why are we gonna do this? Why do we want to move to a different reliability level? So first and foremost, 90% reliability might be a bit too low for some industries. So I have to recall there are industries that require Six Sigma. If you've never heard of it, I hope IE has discussed, at least broached the topic to you. But some industries want a little higher than 90%. So like for example, let's say they want it at 99%, 95%, or maybe 98%. That gives them a higher bit of confidence that their bearings will actually the um, last the lifetime, or at least statistically, most of their bearings will have a better survivability rate in their jobs. So what you do is, first of all, okay, you start with the normal line, which is a reliability of 90%, and then you draw another load line, which behaves the exact same way, but this time it has a higher reliability. Now we call the blue line the rated line, and this orange one here is the design line. Why is it the design line? It's because the application demands higher reliability. So as you can see here, our graph here is life. So this is log life, dimensionless life x, and the y-axis here is logarithmic radial force. So when you go higher in reliability, you actually lower the load life line. So you have a lesser forces that can tolerate. Now, to do this, or rather, as you can see here, this is the same load line behavior. So any equations, any 2 points on this load line here, this design line, can also be related by the previous load line equations. But here, as you can see here, there is just some intricacies. So let's look at the left-hand side. So for the left-hand side, it looks kind of weird. But if we track our graph here, oh, okay. So this is C10, this is C10, and then it is partnered by point B. And point B will have an intersection called dimensionless life XB here. And the second point, the right-hand point, is just the force at point D, and then the life, the dimensionless life at point D. Now, why did we use B in this case? What happened was, so that we can tie this design line to the rated line, what we did was project C10 from the rated line onto the design line. Now, if you do that, if you project the same C10 on a different reliability curve, you end up with a different life. So, like for example, let's say A here is supposed to live at about here. But if you want to use C10 for, let's say, 95% reliability, then of course, in order to have a 5% additional 5% survivability rate, um, the expected life will actually decrease. So when you increase the reliability, again, your life tends to decrease. It's either that or the force that you can subject them to actually decreases. So it's either that. All right. So this is C10. This is dimensionless life. What is dimensionless life? It's just the life of the thing. So XB here is LB divided by L10. So what is L10? We will find out again in the example column here. So as you can see here, we have XB and XD. Now there is also a formula for XB, the other one, and this is where when it comes to changing the reliability, we have to have the experimental the distribution behavior as recorded by the manufacturer. So we cannot jump reliabilities without knowing first the threshold value and all the other parameters. So like you have the scale factor and the shape factor here. So we also have to know that. If the manufacturer cannot provide it, then it's either we buy a lot of bearings from their company and then we perform the test ourselves, or we just kind of assume a particular set of distributions. But again, the latter choice is not very safe. So this is XB. So this is the formula for XB. Normally, okay, so we would know. So let's say we would know our design force. We would know also our design life. So the design side, the right hand side here is what the designers intend, and one way to use this equation is to arrive from the design side what the manufacturers desire to the manufacturer side, which is what rating of bearing should I buy. So based on the design, we figure out what bearing we should buy. So meaning we find out, okay, what C10 rating should we get and whatnot. So in order to cross that bridge, we just do some rearranging. So this is just the same equation, almost. However, there is this new thing here. We'll discuss this later, but I want you to know that this denominator here is actually just XB. So again, this is just XB, XD over XB, all raised to 1 over A. So this is a rearranging of that equation. And if we go to the next slide, we will find out what that letter A sub F is. So A sub F is actually the load application factor. And if you take a quick glance at these descriptions and labels, you'll find out that with increasing precision requirements, when you increase the precision, the application factor decreases. So, for example, if you are in the high precision gearing industry, you'd want your application factor to be as close as 1 to possible. However, to give yourself some allowance, some leeway, like for example here, if you are working at with shop equipment that experiences moderate impacts, for example here, you might be expected to increase the application factor to this level. So again, just take note, when the precision requirements for the application increases for the bearing, your application factor gets closer to 1. Right now, let us move on to an example. All right. So right now, okay. So we have company RPN here, and they want their ball bearings to take on 413-pound force of radial load while running at 300 RPM for 30 kilo hours. So they want 99% reliability for the application, and they want to incorporate a safety factor of 1.2. So here the question is basic. What is C10? If these are my design parameters, what should I look for? What rating should I look for in my bearing manufacturer catalog? So for the specific bearings that your company is looking at, they found out that this essentially describes the entire statistical behavior of your bearing. So you have your shape factor, you have your scaling factor, and then you have your threshold factor. So given all this, what is the C10? Oh, sorry, what is the C10 that you need in order to find what the bearings that you need? Now, this is actually a very straightforward. This is a very plug and play equation, but it pays to understand what we are given here. So this first paragraph here describes the design side. So this is your intention. This one, the third paragraph, is from the manufacturer. So this is their tests. They analyze the statistical distribution of their failure curves, and this is what they got for 99% reliability. 99% reliability. Or rather, they are for multiple reliabilities. We'll check later if this is true. And then lastly, okay, so this is my design. Where is it reflected in the catalog of my supplier or the manufacturer? So what should be our first step? So recall that our equation, our load line equation, behaves like this. So it behaves like this. So then let's check what do we have here right now. So we actually know this. We already know A. What else do we not know? C10 is the unknown. What about the dimensionless numbers? So for the dimensionless numbers, we find the following first. So we get XD. What is XD here? So XD is the emoji. No, it's not. XD is just the design life. So XD is equal to LD over L10. Or rather, no, it should be sans serif L10. So scratch that. Sorry about my the mistake in the notation there. So it's LD over L10. L10 is just 1 million. So LD here is just the standard run-of-the-mill bearing life equation. It's 60 times the number of hours times the RPM. So we have 60 times 30,000 times 300 RPM divided by 10 to the 6, and that is this number. That is our XD. Now, okay, what's next? So A, actually, I checked A, but where is A here? So A is actually in the description of the bearing. So it's a ball bearing. So with bearings, or at least with rolling element bearings, you only have two values for A. So A is either 3 or A is equal to 3.33. If it's a ball bearing, it's definitely A equals 3. So, okay. Oh, wait. Where's D? Do we have to solve for D? Actually, that's a good thing. Let's check if we are actually going to solve for... Oh, we didn't solve for B. Oh, yeah. It's XB. XB is... we can leave that as the unknown. XB here is expounded. Essentially, this is XB. So we don't have to solve for this anymore. So we just check that part. So out of these, we only have one unknown. It's C10. And now we have 540. Your threshold factor, you can plug that in. Your scale factor, plug that in. Your RD is actually 0.99. Yeah, it's 0.99. Plug that in. And you have your shape factor and just plug it in. See, it's just plug and play essentially. So when you're handling an increase in reliability for bearings, the thing that you have to make sure is that you have the description of the Weibull parameters. Unless you have the Weibull parameters, you cannot proceed to this. You cannot proceed with this problem. So I hope that's clear. If we want to jump reliabilities, we need to have an understanding of the statistical behavior. All right. And the answer here is actually 6,700 pound force. This is C10, mind you. This is C10. And our intended load is 413 pound force. That is crazy. That is... So this is at 90%, right? So this is 0.9. And in order to get to 0.99% reliability, meaning there's only 1 out of 100 bearings that will fail after a particular life, you need how much of an increase? This is more than 10 times wait. Yeah, this is more than 10 times the increase. This is crazy. So, right? I hope this example makes it clear. Even a unit's increase in reliability results in a very big jump in the amount of force that you have to tolerate, or at least, uh, yeah, the amount of C10 increase is absurd. So, yeah. That is for differing reliabilities. Now, let's explore this other topic known as equivalent radial load. So when we have bearings that are expected to be actually loaded, we can actually just clump up the actual load into the radial load. We'll get this equivalent radial load FE. And in order to relate these to the radial load properly, we have to define two dimensionless numbers. And these numbers are just force ratios. So here in the left, we have the ratio of the actual, sorry, not actual, it's the actual force over the radial force. This letter V here is just a factor. This is a rotation factor. I'll show you the definition later. On the right, we have our effective. We have our effective force. So this is actually effective radial force over the radial force times your factor V. Now, what we're going to do here is we're going to relate the behavior of the actual force to the effective force that is being felt by the bearing. So take note that this effective force, we can actually use this for our load line equations. So if you recall, if you have C10 LB, oh sorry, oh my bad, LB 1 over A, we can actually use this in this equation here. We can actually use this. Okay, so we're relating actual force and effective force here. Here's the definition. So the rotating factor only has two values. So if the inner ring of the bearing rotates, it's at 1. But if it's the outside that rotates, it's 1.2. Now let me check. Okay, so I'm right. So we can actually relate this way. So yeah, the effective the effective load is kind of like yeah, it is the effective radial load. So if you factor in the actual load, the radial load kind of increases a little bit. Now you may expect some kind of okay, what if scenario? So this is actual force, this is the rate, this is the effective. You might be expecting something like this behavior. However, that is not the case. Upon experimentation, several experimentations, they found out that the relationship between the actual load of the bearing and the effective radial load is kind of like this. I am not sure how to explain this empirical behavior. However, it is what it is. So it is reality. So we have to accept it. So this is kind of like a piecewise function. Again, this is the actual force, and this is effective radial. So there is a point where in the actual load, no matter how much you increase the actual load, the effective radial load would kind of not bother. Like it kind of does not understand what is actual. And then after this intercept here, or rather this abscissa point here, it starts to acknowledge the actual force. Like it just, oh, you're there, so I have to increase as well. So this kind of a nutty behavior here. Let me just go to this graph. Okay, so this one, the piecewise nature is much clearer. So we have two sides of our actual and effective load behavior. Before this point, your effective load, essentially, it's saying that Fe is almost equal to the radial load. So the actual load before this point doesn't really matter. However, once you exceed this value here, then it will start to behave like a line. So perhaps you might be interested. Okay, so what happens? Or rather, what is this? What is this abscissa here? This abscissa is actually this fraction here. It's the actual over what we call the basic static load rating. Basic static is C0. Whoa, okay. So let's keep track. We have C10 and we have C0 or C0. C0 is different in nature to C10. They're both loads, but their source of definition is different. C0 is defined by the dent that a load makes, or the dent that generates a particular dimension of hole. So C10 is an impact base rating, while C10 is more of a reliability rating. So C10, they're both loads, but C10 is based on 90% reliability. C0 is more of, okay, so how much force do we apply so that we can get this size of hole? And that is basically C0. Hold on. Okay. What? Hold on. I'm just gonna erase. Okay, yeah, this is kind of bothering. So all right. I hope it's clear that this is a very piecewise function. So as long as your ratio here of the actual force over the basic static load rating is not exceeded, the actual force is essentially ignored. But after this point, it has to be acknowledged. All right. So okay, so that is the actual definition of E. Do we have any solid values of E? Like do we have numbers? There is we do have numbers. Some contributor I'm not sure if they're actual contributors to Budinas and Nisbet, but they are acknowledged in one way or another. These are the tables that we have to examine. So all right. Now, if you look here, okay, so I am actually incorrect. E is not this ratio, but it is dependent on FA over CO. So there is a dependency. So what you do here is you find where the FA over CO of your application is, and let's say it's just in between two particular numbers. That means you have to interpolate the value of abscissa E here in order to find out what value should you not exceed. So again, you're gonna use FA over CO here to find out what value should you not exceed. And from there, okay, so that will decide what values or what form of equation are you going to use. So it's either you stay in the flat line here, or you go to the linear. Oh, sorry, you go to the linear part of the piecewise function. So just notice here, this is an easy bit. Your floating x to the 0 term here is just 0.56, and y here is multiplied to FA over VFR, yeah, FA over VFR. So this one is increasing while this intercept here is constant. It's 0.56. So right, okay, so this is FA over CO. Where do we get CO? CO is actually found in this table here. So this is CO. You also find the rest of the dimensions of the bearings, particular bearings. I am not sure where Shigley got these ratings specifically. They have to come from a particular manufacturer. Let's just believe that they are well acknowledged in the references for that book. So what you notice here is that there are two kinds of ball bearings in this application. So there are deep groove bearings, so deep groove, and there are angle contact bearings. So in a quick run, deep groove bearings, you can kind of think of them as more of the symmetrical. So they're kind of a symmetrical type of bearing. So this side is symmetrical to this one. While for the angle contact bearings, there is, as you can see here, some asymmetry. There is an asymmetry here and causes the ball bearings to rotate a little bit off axis. And as you can see here, the effect of that difference is reflected in the force that it can tolerate. So C10 and C naught for both of these, they seem to behave. It's like the deep groove one is higher. It's better than the angular contact at low sizes. But if we look at let's check if it's consistent. Oh, okay. So at some point, as you increase in size, the angle contact bearings will perform better. I am not sure if this is consistent for all kinds of deep groove and angle contact bearings, but just notice here is that the deep grooves only perform better in this slot. But if you now compare them to the other rest of the table, the angular contact bearings seem to carry more load. They can carry more effective load, I think. C10 and C0. Alright, just know that, yeah, they have a unique C10 and C0. And now let's go to an application. Right now, so this company, What the Hey? So What the Hey needs bearings which can take on axial and radial load of 400 and 500 respectively. 400, 500 respectively. The outer race remains stationary. Outer. While the inner race is expected to spin at 720 RPM. So What the Hey settles for an SKF 6 to 10 angular contact. So, angular contact ball bearing. So, the model has a static load rating C naught of 4,450 pound force and a catalog rating C10 of 7,900 pound force. Find the design rated life in hours of this bearing. So let's break down the given. This again, design. This is also design. This one is from the manufacturer. So you have inputs from both your team and the manufacturer itself. And we're being tasked, okay, so what is a design like, rated life? So out of the two L's, so I should have used them properly earlier, I mean. It's this one. This is what we are looking for. Excuse me. Sorry about that. Yeah. Curvy L or design life in hours. So, right, the first thing that we need to do is, okay, we have to fill in what's missing. Uh, we have to get to this equation. We have to get to this one. And to get there, we have to find out, okay, what is this? How do we get there? And I believe we'll be able to obtain other parameters that we don't quite know just yet. Let's go along with this problem. So first, okay, we have to find out, okay, what do we need to get here? So just recall that in order to relate axial, radial, and effective force together, we need the following fractions. We need Fe VFR. We need Fa VFR. And we need Fa CO. So let's check. Do we have these? So we have FR. We have FR. We have FA. We have C naught. What about V? So V here is in the description. The outer race remains stationary. That means the inner race is the one that's rotating. If the inner race is rotating, that means your V is equal to 1. What about A? So A here is an angular contact ball bearing. This is not a ruler. So if it's a ball, then it's 3. So right. So from this point on, okay. So we have to go to this curve. Sorry, that is an ugly curve. Don't mind that. So we have to go to this curve. And to go here, we have to solve for these three fractions. So we calculate dimensionless load. FA over C naught comes first. It's this particular value. FA over VFR is this value. So now, sorry about this. I'm gonna clear the screen for a bit so that we don't get a little messy. Okay, so this is FA over CO, FA over VFR. Where is FE? VFR. We will find out later. So our priority for the meantime is finding out what is this. What is this abscissa? Because from there we'll find out if FE over VR is just 1 or if it's increasing. Oh, sorry. So right, to do that, let's go to our table. So I obtained these particular values. Okay, so this is your FA over CO row. This is your abscissa E. So your computed FA over CO is actually in between the following values. And what you can do is interpolate. Oh, why is Y2 here? This is just in advance. This is in advance so that if ever we need to compute for if ever we need to compute for this side, we are ready. So right, so maybe you can try this. Try to interpolate for the value of our abscissa E, and that would be 0.2845. 0.2845. So this is 0.2845, and our FA for VR is way past 0.2845. So that means it's well inside this zone. So we have to compute for our x2 plus y2 FA over VFR. Yep, that's it. So what we do is, of course, interpolate as well, and we will get this value here. So this is the lead up to FE over VFR. So, alright, so we go to the next part. So yes, we use the linear portion. When we say linear portion, it's the one that's not flat. So we perform particular equation. Oh, where does 0.56 come from? It's the default intercept of the line. So the line intercepts at 0.56. It's 0.56 here. Okay, so it's default. 0.56 plus the intercept, the interpolated y, and then we take our fraction, and then we get the following. Oh, we got our FE immediately. That's nice. Okay, so what's next? We try to find out what is the design rated life of our body. So this is the load line equation. Whoa, why is this 10 to the 6? Remember, C10 is paired with the reliability of 0.9. And normally, manufacturers design C10 with 90% reliability for a life of L10 or 10 to the 6. So again, if you are using C10, so this is log life, log F, log L, I suppose. Oh, right, yeah, it's log L. As long as you're on the same line, C10 is associated with L10, is associated with R equals 0.9. So it's a given. When do we break this rule? We break this rule when we have a different reliability. So here C10 is no longer L10. So this is the only circumstance where C10 is not associated with L10. Oh, sorry. But if we stay on the same line of R equals 0.9, we are good. We are good here. So now the only unknown is this one. This is unknown. We know this, and we know A. So what we can do is we can just rearrange the equations. Oh, what happened to L there? So L, this is number of cycles. Oh no, this is, yeah, this is, oh wait. This is number of cycles. This is number of hours. This is RPM. Yeah, this is number of cycles. So cycles, you can expand that to this form, 60 times number of hours times RPM. And what we can do is we can just rearrange this further so that we can get L10. What you can do is, of course, pass, oh, hold on. So what you do is you raise the entire equation by A, so that you can cancel A here, and you raise all the forces by A, so that cancels A as well. And what you can do is you move FE to the other side. Hence, you get this equation here. Yeah, like that. And then your L10 is just here. And that is your LD. So you can manipulate this further, or you can just get the actual value later on. You can use this as X, and then after you solve for this one, you divide it by 60 and your RPM, which is 720. Now you're gonna clear the board. again, I haven't actually been this dexterous with Microsoft PowerPoint Pen in a while. This is computed to 16 140 hours. Is this exact? This is not exact. So what you have to remember here is that sometimes if you try to be precise too much, then you might be no, I'm gonna cancel the train of thought. Sometimes there doesn't need to be a precision level answer in the industry. Like for example, sometimes we'll ask in the exam, okay, so in the exam, two decimal places. At work, usually this is okay. But in the precision world, in the natural sciences research, sig figs will dominate the reign of our of how precise we can be. So how many sig figs do we have here? We have, oh sorry, one, two, three, four, five. So I guess we have one, two, three, four, five maybe here. So I think I rounded off here. I'm not sure if this is the precise one. But yeah, I think I actually used this for the actual precision. So we assume that it's 7900 dot. But yeah, don't be um too queasy about being precise with such big numbers. Sometimes it's not really that worth it. Most of the time, if you try to add precision to your answer, you just end up with actual difficulties in practice. Again, this is just something that we do for the exam to make things easier to check. But in real life, again, the rules are not so clear cut. So that's it actually. This is it for bearings, and I hope you enjoyed this discussion. And I hope to see you again later. Uh, thanks.